We are here today to present CourboSpark, which is an implementation of decision trees for time series on Spark. So I will present it with Simon from Octo Technology, and I am Christophe Saperic from EDF. So this project is part of the Xdata project. So the agenda of the presentation. First, there will be a problem description. So what kind of data do we have? What do we want to do with this data? Then part about the implementation. So we present the algorithm, because we had this algorithm before we move it to a parallelized version. We have a standalone version, so I will present it and what we do. Then I will explain how we move this standalone version to the CourboSpark version, to how we modified MLlib to make it work. The two other sections will be presented by Simon. So it will be about performances and how we configure our clusters, and some feedback about MLlib, Spark, and Scala, and so on, to give you a bit of feedback of how we did this project and what we learned from it, and if you want to do the same, what to take care of. So first, our data. So EDF is an electrical company in France, is the main one. So we are in the process of equipping every old house, so flats, house and so on, with smart meters, which is called linking. So this smart meter will be in few years everywhere, and it will collect data from how much you consume power during the time. So we have your power consumptions. So it will be, then it will arrive in our clusters, and then it will be processed there. So if we crush the numbers, we could have one measure every 10 minutes and 35 million customers. So we speak maybe in 5 or 10 years, and so it will represent a time series of 144 points for every day. So for one year, it would be 1,800 billion records, so about 120 terabytes of data. So now our problem, our data sets. So here we are in the context of supervised classification or regressions. So what we want to do is we have our customers and they are consuming power. We want to understand why the curve is, why someone is more consuming power in the morning, in the afternoon, or in the evening, and maybe during the night, because you have some equipment during the night. And we want to see if we can explain this curve with some explanatory variable. So here is the data set. So we have the load curves that the Linky smart meter will send us. And we have some features that we have about our customers, because we have the CRM and so on. So we have, for example, the contract type, the maximum power you can consume, where he lives, its main equipment type. So in France, maybe it's a bit specific, but we have a lot of electrical equipment, I mean, for warming the house and so on. And if your main one is electrical, it will be much different than if you have your heating, which is gas. So that's a bit specific. So this is our data set, and we'll try to explain these curves using these features. So there is, in data mining, there is many models that can be used. We choose to use decision trees for 3 reasons, because they are easy to understand for if you want to present it to business or to marketing, it's easy to understand. You have the ability to explore the model. So you can start from the root, say, okay, this is the main feature that explain how I spread my curves, and so on, and you can go down and so on to have more details. And you also have the ability to choose the expressivity of the model. If you want something compact, you will maybe just keep this part of the tree. And if you want to have more accuracy, you will have a deeper tree. So when we speak about decision trees, the main, we need to start to build the tree, and we need to find how we split our data. So, for example, you have the root. And in the root, for example, I don't know if it is you have age in your data set, and age is the feature that will help you to split into. You need to find a criteria to see how you can split. So here the split criteria is inertia, and the goal is to find the most different curves depending on exploratory feature. So how do we split? We can use either this criteria, either minimize the curve dispersion. You want your curve when you split into that be close to each other. So it's called intra-inertia. Or you can also do some maximize the differences between average curves, which call the inter-inertia. So you want in your data set in each part of the tree to have the average very far, so that it's really help you to differentiate your load curve. Here is an example of the data. So you have here the power consumption in watts, and you have the time of the day. So we take one feature of the dataset for equipment type, for example. So you have electrical, someone who has electrical heating at home. So you have this kind of curves. We have second customers with this consumption, and we have two other customers with gas. So what we do, we compute the average curves for each modality depending on the equipment. And what we want to find is the features which have the max distance between these curves. So we want to maximize the distance between the average curves. Then we have already an algorithm, because this implementation is already done. We have it for 10 years. And we want to have more curve, more data, and we want to do some parallelization to be able to treat more data. And we are looking what can we reuse from which is existing, and we choose among all these publications. We choose to start from the MLlib decision trees. It's recent. It works on Spark. It's open source. So and it was the first test was working very well on big data sets for classification and regressions. This is a slide to explain how MLing decision trees parallelization works. It's taken from the presentation in Spark Summit last year of MLlib. So what you have, it's an iterative process. You start to build the root, then you build the first level, and then the second level. So first, what you do, you have 3 hosts. You have a CSV file, for example, and it is spread across 3 hosts in your cluster. And what happens is you compute statistics on each of these hosts, and you send it together, these aggregated statistics. So here it will be the average curves. And then when you have all the statistics, you can find what is the best split point. So the best split point here, you find here. It's address none and equal true. And you do it recursively. So then you've built this first root node. So you have these 2 leaves here. You reread all the data. You aggregate statistics. Then you can find this split here, and you continue and go on. And each iteration for one level of the tree. So I will explain a bit more detail with the inertia criteria how it is for the first level. So the step 1, so we have 3 hosts here, as before. We have a numerical feature from 0 to 20. We have our curves. And the first step is to compute the average curves. I use all these curves, and I compute average, and so on each of the hosts. And the next one is one host is chosen to collect all these average curves and find the best split. So this happens here. And we do it on all the features, and we choose the one who has the best inertia. We choose it to split, and so on. So now what we have to do, because we use MLlib, and MLlib couldn't work straight out of the box, so we had to implement some new features. So in MLlib, you have already some criteria, which is entropy and Gini for classification and variance for regression. You have a data structure to store the data, which is called label point, which you have your features on one numerical, which could be the class for classification and a numeric value if you want to do regression. So what we did, we had to implement another criteria, which is the inertia, as we presented before, because we want to compare time series. We have to change the data structure because it's not just a point, but a curve that we as the target variables. So we had to implement time series. It's the same, just different. It's not just a numeric, but time series. We also have some. We also have some issues to do some computation with nominal features because it's time series, so it's a bit different. So we had to implement a specific algorithm for that. I will present it just after. We also add some visualization because we want to see the curves in when you are in the node, when you are in the leaves, and so on. So we had quantiles, how much inertia we lost when we go down in the tree, and number of curves per node, and so on. So now I will explain a bit more in details how we dealt with nominal features. I will first present the current implementation for regression in MLlib, and I will explain you why we couldn't reuse it. So here you have features with 4 modalities, A, B, C, D. And how it works for regression is that you compute the mean and the target for each modality. So here it will be, you compute it, so you have the mean here, 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 and here. And you order them, and you try 3 split points to see how it spreads and how much your criteria give you. So you test 3 partitions, A versus CBD, AC versus BD, ACBD versus C. So if you have 4 features, you try 3 splits. So if you have 100 features, you will try 90 splits, so it's scale linearly. We are happy. Now, we don't have the numeric feature, a target with a numeric feature, but we have a curves, like here. So we have the same A, B, C, D, 4 modalities. We have these 3 average curves. The question now is, how can we order these curves? It's hard to order curves, so we couldn't reuse the algorithm. So one solution could be to try all the bipartition. So you try A versus B, C, D, A, AB versus C, D, and so on. Well, it works nice. It's even the best solution you could think to do. The problem is it's a highly combinatory problem, and it depends on n, the number of modality. So it's O to n and O to 2 per n, and 2 per n after 20, 30, just take ages, like many days to compute. And we plan to have more than 20 or 30 modalities. So what we did is we use agglomerative hierarchical clustering. So you can look in the literature, it exists. We didn't invent anything here. It's a bottom-up approach. The complexity is n post 3. And we don't really expect to have something more than 100. Anyway, with the current implementation, even with 1,000, it will just take a few minutes to compute. So it's not an issue. So how it works is first, I try to find the 2 modalities which are the closest together. And you can see here, they are the closest. And you regroup them. And then here you add, I don't know, 1, 2, 3, 4, 10 modality. And then you have just 9. Then you find this one, you regroup it, you have just 8, 7, and so on. And like that, you compute your bipartition, and you try to find the best splits. So that's it for the first part, but more the algorithm and how we implement these specifics. And now Simon will present you more about detail about performances and Scala and Spark.
Okay, so this is just a very concrete view for you to see how we use the program. So this is exactly the same API than Spark and MLlib. We just have the same signature for the functions. So what you do is define parameters for the algorithm, in particular the maximum depth of the tree. Then you configure the Spark context, so it will be executed in local mode on a yarn cluster or Mesos cluster and so on. You load the data, and with the one-liner, you learn the model. So this is really nice to do machine learning in one line. Now we are going to talk about performances. So distributed systems are really, really hard to test and to tune. Okay, you have a lot of things running. Maybe you don't monitor them, or maybe you even don't know where they are running and what is the impact on performances. You have a lot of parameters to take into consideration: CPU, RAM, IOs on disk, network topology, a lot of stuff. So the first parameter to look into when you're turning a Spark job is the number of executors that you're going to use for your job. So that is the number of JVMs, if you want, and the RAM per executor and the number of cores per executor. So our cluster was a 12-node cluster of a total amount of 300 cores and 300 gigabytes of RAM. And we tried for a constant global capacity of 120 cores and 120 gigabytes of RAM, different combinations. So we found out that the best one was with 60 executors and 2 gigabytes of RAM and 2 cores per executor. So this is not obvious. Maybe you can just imagine that you're going to put 1 executor per machine, and with the maximum RAM and cores for this executor, but maybe this is not the best solution. So you have to make the test, because this is very dependent on many parameters. This is dependent on the kind of workload that you have. Are you just doing big maps, or are you doing a lot of steps with shuffles, reduces? Are you doing something that is very complex, or is it just a full scan of the data set? It's depending on your network topology and the kind of machines that you have. Is it just commodity hardware or big machines? So you have to test it by yourself. So we try to understand why 60 executors, and the first thing we did is study the scalability to the number of containers. So what we did is enhance the number of containers. So each time it's adding computing capacity, RAM and CPU. And this is the number of gigabytes we process every minute with our system. So as you can see, there is clearly an overhead into the framework. After 60 executors on the cluster, even if you add computing capacity, the performance is lower. So that can be explained by a lot of things, in particular network saturation or IOs to disk saturation, locks. Can be explained also because if you add more containers, you need to manage them, to orchestrate them, to monitor them, they have to communicate between each other and so on. So this is the same chart, but with the red line that is the linear expectation. So as you can see, we don't meet this expectation at all. And every time you add containers, in fact, you lower the performance and the efficiency for a single container. So this is the number of gigabytes you process per minute per container. So when there are only 2 on the cluster, okay, they are RP, they are alone, they can really be efficient, but the more you add containers, the more a single container is less powerful. So 60 containers on a cluster, it can be nice if you are alone on it, but if you are on multi-tenant platform, for example, maybe you don't want to waste resources and you want just to have 1 executor per machine and let the resources for somebody else. Okay, now we study the scalability to the number of lines. So you have multiple ways to grow your data set, and as it is a big data paradigm, we want to analyze the most client as possible. And so what we did is take a data set and replicate it line by line. So these are different sizes of data set, but every time this is the same number of features with the same features and the same data in, but just with more lines. So this goes from 100 gigabytes to 1 terabyte. And as you can see, whatever the data set is, we process the same number of gigabytes every minute with the system. So that means that it really scales linearly. If you want to process more data, you just have to wait more. Or maybe if not patient, you have to add nodes to your cluster, and you will process it in a lower time. So if I want to process 10 terabytes, it's okay. I have the same computing capacity, and I just have to wait. It's not exploding in complexity. So this is about framework stability. This is really important. This is the distribution of the performances on all the tests that we did. So we did really a lot of tests. We did 10 tests for each configuration to study the variance. And we did a lot of configurations on a lot of different data sets. So different kind of data, categorical continuous variables on different type of individuals, with different configuration, depth of trees, bin sizes, and so on. So as you can see, most of the time you can expect the system is going to process between 7 gigabytes per minute and 8.5 gigabytes per minute. So this is really predictable, and you don't have surprises. When you run a job, you know that it is going to go this at its pace. Okay, scalability to columns. So this is another important topic. Maybe all the variance and all the information is not gathered into 1 or 3 variables, but maybe this is a kind of data that is made of weak signals, and you need to study a lot of variables to really make a good prediction. So you don't need a PhD to see that it's not scaling with the number of columns. So this is with 10 columns, this is 100 columns, and this is with 1,000. The reason for that is that the computation to find the best split is made on a single machine. So as Christophe explained, you compute all the statistics, and then you gather them on single node to find out which is the variable that is having the best split. And if it's on a single machine, it can scale. Okay. This is with modalities. So for example, if you take the eye color, it can be blue, green, brown, whatever. And so this is variables that take multiple values, and same thing, it doesn't scale because the hierarchical clustering is done on the single machine when you try to find the best split. So here, after 500 modalities, it's really taking more time to do the same kind of processing. So these are virtual value that we generated to really push the system and to find the limits. And when we study a real-life data set, the scaling is okay. So this is just a screenshot to show you that during this find the best split phase, we only have one active task on the cluster. So if it's not distributed, it just can't scale. So real-life data set performance test. So real-life, it means that it's real data, it's realistic data with realistic number of modalities, features, type of features, numeric and categorical, and so on. So here with very realistic data, we scale well up to 1 terabyte and for 400 gigabytes. So in few hours. So this is really great to have framework like this, like MLlib, to do machine learning at this scale. Few years ago, back then, it was really hard to have a system so performing and to really leverage the big data analysis. Okay, and when you do big data, you don't just want to do classic ETL at scale. You want to really make statistical inference. And I think Spark MLlib is one of the greatest projects out there to do that. Just to have you an idea of the amount of data, this is 1,000 million load curves. So for example, a classic algorithm you are looking into when you start a machine learning project, it can be SVMs. So they are well known of the literacy. And one factor to say, okay, I'm not going to use SVM is the number of lines and individuals. And sometimes when it's 10,000 lines, you say, okay, I'm not going to use SVM, it won't scale. Here we have 1,000 million lines, so it's really big data. Okay, some information on the tuning. So these are the parameters you are going to look into when you debug or when you try to tune a Spark job. So most of the time, because Spark is a memory framework, you will have memory errors. So this is really the errors that you will have most of the time. It's kind of full to debug, but these first parameters, default parallelism, it defines the number of tasks that you are going to execute on the cluster. And because the data is distributed, the more tasks you will have, the more chunks of data you will have, and the smaller they will be. So if they are smaller, they will fit better into your memory, and you will avoid memory errors. I think the default parameter is like 3 or 4 tasks per course that you have in the cluster, and you can safely go to 6 or 7. During the project, I even defined this parameter to 2,000 or 4,000 tasks. This is not an issue. Spark is really agile in managing the life cycle of the task. So you can really increase this parameter. This is safe, and this is well-performing. This is not a problem to have a lot of tasks. Executor memory, so this is very stupid, but if you have memory errors, just give more memory to your executor. Memory fraction is a bit smarter. So memory fraction is a portion of the memory that the JVM will be able to use to cache the RDDs. So if you have data structures into your Scala code to make decisions or to make custom stuff, if you need a lot of them and you have memory errors, maybe you can lower this parameter to have RDDs spilled to disk. So it will be less performing. You will do a lot of streaming to disk, but at the same time, you will have more space into your JVM for your custom and personal data structures. And the last one is AK frame size. It's a parameter that you want to increase when you do big collect operations. So collect operations are when you want to get back your RDD to a single node to do some computation with it. So this is an operation that we do when we try to find the best split. So typically, as we said, we have a lot of columns and time series, so the data structure are kind of big, and we had to increase this parameter to scale well. Okay, some feedbacks on Spark. So as a developer, it's really nice to have a flawless transition from a local to a cluster mode. I've never been surprised with some code that I wrote when going into a cluster mode. And I cannot say the same thing for every big data framework that I've worked with. You have a debug mode with an IDE, so you can put breakpoints, you can go line by line inspection, you can evaluate what is in a given variable during the running of the algorithm. So it is really, really nice to go in debug, in particular with this kind of code that is kind of complex. On the other side, good performances, they really need knowledge. Both on the API, so what are the different functions, what is a map partition, what is a partition by, a hash partitioner, why is an aggregate by is performing better than a group by and a reduce. And you also need the knowledge of the parameters, so parameters for tuning that I just mentioned the slide before. So here just a little word about Scala. So this is the kind of code you will have in your project if you don't look after code quality. So Scala is a very, very permissive and powerful and rich language. So if you add to that you are doing distributed computing, you will end up with big one-liners with a lot of dynamic functions, and it just looks like video games cheat code. And you really have to care about quality code during your project. For the data scientist, I find the vanilla, the classic Spark API is not very data-oriented. So even to do just a select on the column is not obvious. But at the same time, now we have Spark SQL, and now the data frames that are coming that are implementing the same methods you can find in R or maybe in Python pandas. So this is why I like Spark. It's because I think the contributors have a great vision of what data scientists need to be efficient in their everyday work. So now we'll have a group by function, maybe replacement for missing values, and so on. What is really nice, and yeah, there is a session about that later, is the combination of IPython and PySpark. So PySpark is the Python API for Spark, and IPython is the most well-known environment for data scientists working in Python. So what you can do with that is have a really agile working environment where you can run a Spark job with a big data set, get results back into memory, put them into a data frame, do some plotting, some data visualization, understand the data, modifying your big data job, then you get back the results, you put it into a data frame, you do some modification, get it back to Spark, you use it as a lookup table to make a join, and so on and so on. So this is, I think this is the future. And last consideration is about two kinds of machine learning approach that I know. One is feature engineering, and this is the one I know the most, is saying that most of the time you have the APIs to do the processing. So you have R, you have Spark MLlib, you have H2O, you have R, whatever. And just your work as a data scientist is to clean the data and create new features to add a signal to predict the target. A second way to approach machine learning is model engineering. It is when you really create a specific model to your problem, because your data is social data, it's graph data, it's time series, and so on. And I always thought this model engineering kind of machine learning is just for researchers. This is too complicated to code your own custom code. And in fact, this is not. This is something really doable, and I advise you to try to do it. If you have a particular problem, you can write your own code and tackle your problems. Concerning operations, I think Spark is better than MapReduce for performances, fault tolerance, it retries failed tasks and stuff like that. Also, performances are really predictable for tested code. So if you have different environments, for example, a production environment, a test environment, a pre-production environment, if you know that you scale well on your pre-production environment, you can safely assume that it will behave the same on the production environment. So this is really important when you have really big data set and different environments. It is yarn, so you have scheduling, monitoring, and so on for free. On the other side, you have a lot of releases, and the ML code is really evolving fast, so you get to have some criticism about upgrades and versions. So as a conclusion, I really think Spark is enabling machine learning at scale easily for data scientists. And I think the guys that are contributing to the project have really a good vision of what needs big data for now. Future works, if you want to talk about that, we'll talk about after the session if you want to. Thank you.
Any questions?
I missed the real specific business goal of this exercise. So what do you want to predict? And the second question is, why is it that it was now better by using big data than it was before? Because you could also take a sample of this 1 billion, I don't know, and was it really necessary to work in this with big data?
So good questions. In fact, as I explained at the beginning, it's these smart meters are developing, and here it's R&D from EDF, so it's more to see what we can do if we have more curves later. For now, we don't have that many real data, so I cannot really tell you if sampling will be enough or not. We will have to test it, but we wanted to see how we could manage to reuse our algorithm that we developed 10 years ago and to make it to work at scale. And yeah, maybe sampling will do the trick, but I don't know. It really depends on data sets.
Yeah, more data is just more accuracy for the models in general. You want to really give the more data as you can add to your model all the time.
We are sure not to have bias using sampling, but we can do good sampling, so it's not. And about the problem, the first question. So it's first, this tool is more for exploratory purpose. It's more like I want to understand why my customers have such a load curves. We are doing a lot of work about load curves in EDF. This is just a very, very small part of it. And sometimes we also have some kind of k-means, code and map, and so on. And this one, if we have descriptive features, it's nice to understand why these kind of customers will consume that way. And maybe it can help the marketing to see, okay, we have that many customers which are there and are consuming a lot of power in the morning. I don't know, we have nuclear plants at some place, some other place maybe you have more, call it, photovoltaic. You have different, Aeolian, I don't remember the solar wind stuff. So that's it. It's more exploratory than really doing predictions here.
What is your experience working with Spark SQL? Because we had several issues on the compatibility with the JDBC drivers. Have you made any experience around that?
Which drivers?
JDBC.
JDBC. Here we have a CSV file, so we just use plain CSV file to load the data in RDDs and so on. So
you're not using JDBC to access Spark SQL?
No, we don't use Spark SQL here.
Spark SQL is kind of new, so yeah, it's not very stable at the moment. So you have missing stuff like dates and so on. Yeah. So if you have to give it some time, I think.
And if you don't mind, so data coming from smart meters are general, I would say, on an unstructured or let's say not a normalized data structure. Have you made a decision on which data structure fits best? Is it just CSV, or have you moved to JSON on that? Or
no, it's. I mean, I don't have the whole knowledge here. All the data we were working here, as I said, we don't have this data now, so it's generated data. You know, we built a fake tree and we generate data randomly in the tree and so on. Then there is a lot of normalization, encryption about the smart data and so on. I know there is a lot of work going on, and it's trying to speak between different countries and so on. So I can't give any details about specific, but there are a lot of works concerning that.
I think there are plenty of time series-oriented time series. I think Cassandra is doing the job. You also have implementations on HBase for time series. So.
Thank you for presentation and sharing this with us. I was wondering, just in your context as a researcher, have you ever tried to experiment to see if we run this decision tree on one node, giving it a lot of memory with traditional data mining methods like using sklearn and this kind of libraries, and doing it with Spark in many nodes? What is the percentage in accuracy of the model that we win by doing it in a parallel way than doing it in one node with a big computer, for instance?
Which one?
Yeah, we didn't.
Just worked on it, so I will let it answer it.
Yeah, we didn't try that. In fact, I think the Scalability API is way more richer than the Spark MLlib API. So I think the algorithm is more well-tuned. You can define the tree depth. You can define different ways to do regressions. It should be something to test, but I think the classic data scientist API are richer at the moment. So I think the accuracy would be better for the same data.
Yeah. I mean, if you use exactly the same data sets, I mean, let's say I don't know 1 million on each. In fact, it's not an approximation algorithm we did here. It's exactly the same algorithm. The good part about the inertia criteria, it's all additive and commutative. So you can calculate just partially the statistics on one node and aggregate them, and you are not losing any accuracy there. So it's the model built. We tried both some data sets, and both on the parallelized version and the other version we had before, and the results are the same. So we don't lose any accuracy. No, there was a classic Java implementation of this project before we started. So we compared the results to ensure that we had exactly the same trees constructed built on the same data. But the accuracy is of course the same. And here the algorithm doesn't have some auto-pruning like you have in decision tree classically, so it's just continue to grow. So yeah, it would make more sense that you can do maybe overfitting. But here, both algorithms, in any cases, will overfit. So usually we don't have to go that far.
Did you experiment with Spark streaming and online algorithms?
Not in this particular project, but I tried out on the project, yeah.
Thank you for your attention.